Good afternoon. Thank you all for coming to the SETI talk today. Our speaker today is my good friend and known to many of you since he is often in my position introducing the speaker, Matija. Matija was educated at the University of Belgrade and at Cornell University, which is where I first met him as we shared the same set of mentors. Since then, he's gone on to a very promising career, and in fact, just a couple years ago, he was given the great honor of being recognized with the Urey Prize, which is given by the American Astronomical Society to recognize early career achievement in planetary science. Matija has now been on the research staff here at the SETI Institute for the last 5 years, and he is here to speak to us about orbital dynamics suggests a recent formation of Saturn's moons. So let's welcome Matija.
Thanks, Matt. Before I get down to business of Saturn's moons, I want to remind you of the date. It's April 12th, so it's 55 years since the first crewed spaceflight. Okay, so now the talk. So this talk will have lots of orbital dynamics, and I try to make it painless. So first I'll talk about Saturnian system, then a bit about orbits and resonances and tides. Then I'll mention how tidal heating of Enceladus, which has been in news a lot, actually can tell us something about the origin of the system. And then I'll come to my own work, which is looking at the past orbital resonances between Saturnian moons and how they can constrain the age of the system. And then I'll speculate a bit what the origin of the present set of moons is. And you know the answer if I have to say current moons, which means that there have been other ones, right? So these are the major moons of Saturn. I'm mostly going to be talking about these, but I wanted to put this image, which is to scale, just to show that most of the mass, more than 95% of the mass, is in Titan, which has atmosphere and is awesome, but I'm not going to talk about it today. So I'm going to talk about these 5 moons, actually mostly these 3, the bigger of the inner moons. And then, so this is to scale obviously in size, but not in orbital distance. And if you put it to scale to orbital distance, it looks like this, including the planet of the rings. They're kind of all close to, within several Saturn radii of Saturn, and these 3 have most of the mass, that is Dione and Rhea. And the rings are interior to them. Okay, so before it came, the question arose up about the age of the moons. The age of the rings has been debated, hotly debated subject for a long time. And there are 2 principal lines of argument that have been used to argue that rings might be much younger than the planet. So one is dynamical, that the rings would spread due to mutual collisions way outside their present location over about 100 million years. And the other was that they will get polluted by infalling dust, cometary dust, and which would change their pure ice composition over much shorter than billions of years. And we are fortunate here to have Jeff Cuzzi in the audience, who worked on this problem, and also our own Paul Estrada from SETI Institute has been involved in this. So this is the rings as opposed to the moons. People have been saying the rings might be young for a long time, and I think I have something to contribute by studying the moons. And I'm going to be mentioning a lot Keplerian orbits, named after this guy. So apart from orbits and dynamics, he was into lots of strange stuff, including astrology. And in this book, Harmonices Mundi, he talks about the music of the spheres a lot, before he gets down to the business of the third Kepler's law, which we all know and love. So I'll try explaining some of the stuff happening in the Saturnian system in terms of music of the spheres. Let's see how it goes. Okay, so here is a Keplerian orbit. You have an orbit in space, and if the central body is a point mass or something that's perfectly spherical, the orbit will go on forever. So you can say that it's a single note, and for the moons of Saturn, it's a high note, because they go around relatively fast, every couple of days. And the orbit will stay fixed in space. The plane would not change. The direction of the long axis would not change. But if you introduce non-spherical shape of the inner body, and if you noticed in that picture of Saturn, it was quite a bit squished. It's a bit masked by the rings, but the planet itself is really not round. It's pretty squished to the poles. If you introduce that, the Keplerian orbits around it will start moving around. And there are two types of motion. There is the forward shifting of the long axis in the plane of the orbit. Forward means in the direction of orbital motion. Here it's counterclockwise throughout, but the important thing is it's in the same direction as the body orbits. While the plane of the orbit will shift, it's harder to draw, opposite direction of orbital motion around the plane of symmetry, which in this case is equator. And these two motions are much slower than the orbital motion. This is years as opposed to days. And the interesting part is that these two motions are in the opposite directions, but they're about equal. And I would call them very low notes because they take years to happen. So then when you have multiple moons, you can have them be a part of a harmonic series because their orbital periods are simple ratios of each other. And the most prominent case are Enceladus and Dione, two moons which have orbital periods. If you do the math, they have ratio of 1 to 2. It doesn't have to be a whole number. It can be a simple fraction like 3 to 2 or 4 to 3 and so on. And this has profound implications for the orbits of bodies. So here is a plot of what happens close to the resonance. So this is the ratio, orbital period ratio. So Enceladus being closer to Saturn is here, and being further out from Saturn is there. And here it has the orbital period that's exactly half of Dione's. And when the two bodies are very close to the resonance, that means that there is a beating between their periods, which has a very long period, and it's infinite right here. But here is a very long period that is associated with what we call negative frequencies, going against orbital motion. So it gets in sync with the motion of the orbital plane, which is backwards. And orbital plane, the position of the orbital plane is intimately connected to its inclination. So if you start messing with the orbital plane, you can change the inclination of that plane. So resonance close by actually consists of two sets of resonances. The interior ones that, if Enceladus moves out, would meet first, that change the orbital plane inclination, and the ones further out are in sync with the slow motion of the long axis of the orbit and can change the eccentricity of the orbit. And why would orbital periods change? Well, that's because these bodies are not perfect, and as they interact with each other, energy is lost and the orbits drift. If you have a fast rotating planet that rotates much faster than the moons go around, and this is true for both Earth and Saturn. Saturn spins about every 11 hours. So Saturn is slightly egg-shaped in many directions because of the tidal fields of its many moons. So let's just consider one moon and the egg-shaped figure of Saturn it creates with its tides. If Saturn was a perfectly elastic body, if it would react to all the forces acting on it instantaneously, the egg shape would always point toward the moon. But since it's spinning and the egg shape lags behind the forces acting on Saturn, you have this tidal bulge ahead of the moon, torquing the moon forward because the bulge itself has its own gravity field. And if you push something forward in its orbit, it's going to gain altitude. And orbit gets bigger and has more energy. There is no such thing as free lunch. Energy has to come from somewhere. And it comes from the spin of the planet. In case of Saturn, we don't have to worry about it. Saturn is so much bigger than its moons, and its spin has practically infinite amount of energy, so it will never slow down, really. But that's where the energy comes from. And all the moons will move out. And the inner moons move out much faster than outer moons, because these forces are very strongly dependent on distance. Now, the moon itself is also subject to tidal forces of the planet. Moons typically rotate with the same face facing the planet. So if their orbit was round, it would always have the same relative position towards the planet. But if the orbit is eccentric, this egg-shaped shape of the moon would vary in intensity. Like when it's closer to the planet, planetary forces are stronger, and when stretch it out into a more elongated egg, which then goes back into a more round-shaped apocenter. This flexing of the moon, because it's also not a perfectly elastic ball, creates energy. Well, liberates energy from the orbit. And the end state would be to damp eccentricity. The orbit will become round, but while the energy is coming out as heat, you can have this, if you're in a resonance, you can have a equilibrium between different kinds of tides. So I talked about Saturn tides, how they push moons out. And in this plot, which is distance versus eccentricity, the moon's tides want to push it down towards circular orbits. So these are circular orbits, these are eccentric orbits, this is closer in, this is further out. But when you enter into a resonance, like a resonance with Dione, the Saturn tides push you to the resonance, and then you can get stuck. And you usually get stuck going in one direction and not in the other. And it's way too complicated to explain now. But if you do get stuck, only way you can go is up towards higher eccentricities, and that's what happens in the resonance. But eventually, you get so eccentric, and the flexing of Enceladus creates so much heat that those tides want to damp eccentricity. So you can be in a balance where you don't move on this plot. Saturn tides want to push you into the resonance, but deeper into the resonance is up, and Enceladus tides try to damp eccentricity. And the end result is that Enceladus gets hot on the inside. And the ultimate source of this heat is the spin of Saturn. And the energy is transferred through the tides of Saturn, through the resonance, into Enceladus. Now the problem is, we thought we had some idea of how strong the tides of Saturn pushing Enceladus into the resonance are. And 10 times too much heat is coming from Enceladus. So this tells us that something is wrong in our understanding of the system. This is assuming equilibrium, which might or might not be true. And how did we think we know how strong the tides are? Well, we could only guess. But one hard limit people thought they could limit to how strong the tides are is that they shouldn't have moved the moons more than they could take over the age of the solar system. So this is a nice paper by Jenny Meyer and Jack Wisdom, but this plot can be found in textbooks. You can extrapolate back. These are the 5 moons. You can extrapolate back and see where they were billions of years ago. And by tweaking how strong the tides are, you can make them not get into forbidden zones over 4 billion years. And forbidden zone is this synchronous orbit, which is the distance around Saturn at which you orbit every 11 hours. And at this point, the moon catches up with the rotation. And interior to it, you're going to spiral in rather than out. So Mimas could have never been interior to this distance. And that gives us some estimate of how strong the tides are. And there are all kinds of numbers and quantities used to quantify that. Doesn't matter. But this is one rate, and what comes out of Enceladus indicates that the tides might be 10 times stronger. So maybe it was not in equilibrium. That was what people thought for a couple of years. And then came this paper by a group based in France. So what they did was look at the observations of Saturn's moons over 100 years and try to figure out if their orbital periods are changing. And they got a result. And when they combine results for all of the moons, they get something that's 3 sigma different from 0. They actually have a detection. And it looks like the orbits are changing about 10 times faster than what we thought from the previous slide, where the rate was induced, thinking that moons must be as old as the solar system. So there was also skepticism about this, but if you assume equilibrium, this line, and now this is a weird way you do numbers. Strong tides are here, weak tides are on this side. And the vertical is just how much heat you get from Enceladus. So if tides are stronger in equilibrium, you can get more. So you assume equilibrium of Enceladus in the resonance, and this is the result of Lenné et al. Paper. And so you have the result, you assume equilibrium, and you get the right heat flow out. So this was interesting. So maybe tides are much stronger than we thought. But that gives us another problem. How old are the moons then? They cannot be as old as the solar system. So this last time I showed this, it had a 4.5 billion year timescale, but now we have to think of it as more like a 500 million year timescale. And that's where my work comes in. I was thinking, okay, this is an interesting question, and is there anything we can figure out by simulating past evolution of the moons? Because that's what I do. And as you can see, in the past, they've crossed all these resonances on the way to where they're now. And maybe by checking these resonances, we can see if they happened or not, and how good our estimates of the past are. So the first resonance I looked at is the very important 2 to 3 Tethys Dione resonance. And should have happened about 100 million years ago. So we're showing these plots, which are eccentricity and inclinations versus time. So this is how eccentric the orbit is and how inclined it is. And I start just before the resonance, and both orbits are round and in plane of Saturn's equator. So the first thing that happens for a long time is only that inclination of Tethys goes up. On one of the previous slides, I showed that you meet inclination resonances first. So this is one of those, and this is capture. So if you could see it in the distance plot, the distance would be the same, basically, because, actually, the period ratio would be the same because 2 moons are locked in the resonance. And what happens over time is that Tethys gets more and more inclined. Gets to the point where the resonance spills over, because I didn't show it before. Those resonances, the set of closed resonances next to each other have thicknesses, and thickness depends on inclination and eccentricities. So at this point, one of these resonances gets fat, starts overlapping with the others, and it's free for all. So you can see eccentricity of both bodies and inclinations of both bodies start interacting strongly. And then you cross the whole forest of resonances and get out. Now, you have satellite tides damping eccentricity. So that's what will happen. Eccentricity will go away, and now orbits are mostly round. Inclinations do not. For these moons, inclinations stay forever. So by looking at the end inclinations, we can figure out if this resonance happened or not. And the red line shows current inclinations, and you can see what the end state of the simulation is. We get way too much inclination. It should be many degrees for Tethys, and a good chunk of degree for Dione, but what we see is almost nothing for Dione and 1 degree for Tethys. And we run this with different initial conditions. We started them inclined right away to see if they can jump through the resonance. No, you always get too much inclination for both Tethys and Dione. So one way to look at the results, you can plot what the end state for inclination of Tethys is versus Dione. These are our simulations. Each of these took weeks. And this is the real system in this corner. And there might be processes that can redistribute inclinations between the two of them. So anywhere along this line could probably be OK, but you're nowhere near it. This is a log plot. So we always get too much inclination for both moons. So the only conclusion we can have is that this resonance didn't happen. So this reconstruction of the past, which is basically starting from the present and going back in the past, should not be pushed past this resonance because the system formed somewhere after it. Now we are fortunate that after this resonance between Tethys and Dione, we have a next resonance between Dione and Rhea, 3 to 5. So we can test that. Did this one happen? And here I'm showing all 3 moons. Ignore Tethys for now. You can get the usual pattern. The inner moon, Dione, gets some inclination. Then it starts spilling over into eccentricities. You get chaos for a while. And you exit the resonance here, and then something happens to Tethys. So you can divide this into 3 stages. So the red part, you can see inclination of Dione growing. That means the 2 are tied in the resonance, and inclination of Dione is growing until it spills over into neighboring resonances. The blue is free for all. Dione and Rhea exchange eccentricities, inclinations, get excited. But then they exit the resonance. There is a little white patch that is outside. And then Rhea doesn't do anything, but Dione and Tethys start doing interesting things. And what they're doing here is they're participating in so-called secular resonance. And when I talked about slow motion of orbits in space, the long axis move forward and the orbital planes move backward, and about the same rate. So if you add these two motions, if you kind of have a midpoint between where the nodes have moved and where the long axis have moved, that line would move much slower than the orbits itself, the orbits themselves. And this is kind of infrasound of the spheres, because you take two very slow things, add them together, and you get a very long period, thousands of years. And these two periods, the addition of these two motions, one forward, one backwards, are in resonance in this case. That means that the periods are the same for Tethys and Dione. And this was impossible to see on pen and paper. This came out of a computer, and I was amazed that it worked that way. So why does it happen right after this resonance between Dione and Rhea? This wasn't in the original plot. We are here, right past the resonance, that all happened, and then out of nowhere comes the secular resonance with Tethys. Well, that's because the precession of Dione is affected by the proximity to the resonance with Rhea. And the way to think about it is what I've plotted here is this infrasound of the spheres, that very, very slow period. And all it depends on usually is how far you're from Saturn. Tethys has period about 5,000 years, Dione has 20,000 years, so it just gets slower and slower as you go further out. However, if you're close to a resonance, it induces perturbation to this period. It slows down before and speeds up right after. So Dione is right next to the resonance with Rhea, the third moon, which is kind of outside perturbation here. So this smooth fall off of this frequency is perturbed by there being a resonance, and then Dione is right on this place where it's speeded up. And if you compare where Tethys is and when Dione is, they have the equal precession frequencies. Or you can call it super precession frequencies, because it's a difference between two precession periods. And they're in secular resonance. So what happens here, since these two are added together, that is the precession of the long axis and that of the node, the eccentricity inclination have to do the same thing. So they go up for Tethys, both inclination and eccentricity, and go down for Dione. Dione was excited because it just went through a resonance. So it can hand over its inclination and eccentricity to Tethys. And that's what happens here. Eventually, eccentricities will damp, but inclinations stay. And we get pretty close to where we should be. You can see that Tethys gets its 1 degree inclination by having it handed over from Dione. Dione almost loses it. We don't quite go to zero. The secular resonance breaks because we run out of eccentricity of Dione. If eccentricity was a bit higher and inclination a bit lower, we would actually run out of inclination because they have to fall off in sync. And Rhea doesn't do anything in that part. But just the resonance with Dione itself gives it about the right kick. Here we got about 1/4 of the degree, and actually we should be at 1/3 of a degree. But this is a very good explanation of how these three moons got inclined. First, these two cross the resonance, and then these two cross the secular resonance so the one that has no inclination now handed all the inclination to the other one that has all the inclination. So this pattern, which was really confusing before, makes perfect sense now. So we come back to our master plot of the path of the moons. So the resonance at about 100 million years didn't happen, but the one right after that did happen. So very neatly, we can bracket the age of the system in relative terms to have started between these resonances. And in absolute terms, taking into account Enceladus and the French observations, it gives us 100 million year absolute age. Now, 100 million years sounds like a lot, right? And for astronomers, that's not. We deal with billions of years. And okay, Earth has changed a bit since then. Like, this was late Cretaceous. So here is Spinosaurus is about that age, which I had to look up. But compared to the billions of years of Earth's history, that's nothing. So how can you form moons that late? And presumably the rings, because many people will be happy to hear the rings are young. But still, how you do it? Well, we come to another resonance as usual. And if you look at our 3 major moons that we dealt with before, here are the actual periods of their precession. So these are basic precession periods at which the long axis moves forward and the plane of the orbit moves backwards. There are 5, 11 years, and 35 years. And Rhea, which has most of the mass, is kind of close to another important period in the system. So we are orbiting Saturn, right? So there is an important period, about 30 years, which is Saturn's year. And if a moon was right here, interior to Rhea, its orbit would precess in space once every 25.5 years and get in the semi-secular resonance with the Sun, or Saturn, depending on how you look at it. So the way it looks, and don't worry, this is a Ptolemaic plot. Saturn is the center of the universe with Sun going around it, but it's easier to figure it out that way. Because then you have both the moon and the Sun going around the same center. So what you have is the long axis of the orbit of the moon is moving forward at 30 years, but so the Sun appears to be moving around at 30 years. So the angle between the long axis of the moon's orbit and the Sun can be fixed. And since they have the same orientation for the longest time, that means that they can, the interaction between the two can be very strong. And the bottom line is that the moon's eccentricity can get big. But you rarely have just one moon there. You have a bunch of them, and they often are in resonances, because if they move them around, they get stuck in resonances eventually. So you put in another moon, and so the music of the spheres turns into a whole band of the spheres, because you have the Sun, the two moons interacting through the mean motion resonance, what we call it, just the regular resonance where the period ratio is integer. But the outer moon also has the long axis locked to the Sun, and they all exchange energy and angular momentum, which is bad news for the moons, because the moons are much smaller than the Sun, so they do not have much of angular momentum, and they cannot take much. So the Sun can make them eccentric and have them cross each other's orbit. And once they cross each other's orbits, that's it. They'll collide, and actually quite fast. And this is not just a cartoon. Here is a simulation of that happening. We have, I didn't plot their orbital distances. I plotted the orbital distance of the outer moon. I call it pseudo-Rhea because it's close to the orbit of Rhea. And the inner moon catches up with it. This is not where it is, but this is where something that has 4/3 of its orbital period is, where the resonance with it is. So the outer moon and the resonance with the inner moon approach each other, and they get locked because the inner and outer moon are in resonance. Go on for a while, and then their orbits go wild. You can see that their orbital distance varies a lot on top of each other, and eventually they collide. And this is where the outer moon has the long axis locked to the Sun, and it gets very eccentric, and then passes some of that to the inner moon. And because it's 3 bodies interacting, it's chaotic. You cannot get a stable solution. They'll just keep exchanging eccentricities until they collide. So the music of the spheres turns into a cat walking on a piano, because that's what it is when you form a huge disk. And so most of the mass will be where the 2 big moons were. There could be some smaller moons around, but as the disk is expanding due to the mutual collisions, smaller moons will get pushed around. And if they get pushed too close to the planet, tidal forces will destroy them, pull them into a ring, or debris itself can make a ring. On the outside, fragments can be pushed against Titan. And if you have a very fast expansion of a ring, possibly pushing moons around, that can induce eccentricity of Titan. Titan's orbit is too eccentric, and there has been argument for a long time that tides within Titan should have damped it. So that could be part of our recent event. So we make rings. The inner region is where the so-called Roche limit is. So the tides of Saturn prevent moons from forming. So you will have rings there. Everywhere else, new moons should form. guess I was speaking faster than I thought. There'll be time for questions, I guess. So we come to our conclusions, and that is that I've simulated the past evolution of Saturn's moons, Tethys, Dione, and Rhea, and by looking at what resonances between them happened in the past and which didn't, you can figure out the relative age of the system in terms of orbital shifts. But then you can connect that to the absolute age in years using results from Enceladus, because Enceladus gives us the absolute force by which it is being pushed into resonance through its heat flow. And you can also use the astrometric observations, which agree with both Enceladus and some of the recent Cassini data. So every way you look at it, the age of the moons comes out to be 100 million years. And then the speculation is that the previous moons of Saturn looked a lot like the present ones, with the bigger ones being out there, further out, and that they might have been destroyed because the biggest one of them ran into this resonance with the sun, where its precession period was 1 Saturn year. And it's a strong resonance, and so far it's the only thing I could find that could destroy the whole system. And this thing could have happened more than once in the past. So Saturn might have had rings on and off over its history. Thank you.
All right, thank you, Matija. We have time for questions. Please wait for me to come with the microphone since we are recording this.
Yeah, a question from Dave Morrison, who doesn't know much about resonances. You say there could have been an earlier set of moons.
Yeah.
But if it was anything like this set, you're now talking about a sequence of 10, 20, 30 sets over history. Does that make any sense? Where would the material come from?
The present set is probably stable for 1 billion years or so. So there were only a few. We are still lucky to catch it soon after destruction.
I still then would ask where the material has come from for even a few successive sets of moons and rings.
It doesn't go anywhere, really, between reaccretion, unless you can throw some at Titan. It's possible that the inner moons form from giant rings early on. If you look at the distance at which Rhea is now, a moon with that mass should get as far as Rhea is now on the edge of the solar system, using the tides we have. So it's possible that the original system was very compact. It has evolved over with tides over age of the solar system. And each successive iteration was bigger and lived also longer. So it's really hard to both gain and lose mass or angular momentum. Those two are very, very intimately connected. So you can't just throw that mass into the planet. It wouldn't work because it has too much angular momentum. It wouldn't like to do that. And it's very hard to throw too much of it at Titan, either to be accreted or ejected from the system. So the moons are most of the mass is fated to go through recycling and end up the same way.
So a couple of implications that I thought of. One is that this makes life in ice oceans like Enceladus pretty unlikely if it's only 100 million years old. And also, have you run any simulations on the future, like where this set is going for the next 900 billion years or million years, and what happens after 1 billion years and it goes kablooey again?
I have not run the future. It's a very well-defined problem, so it would be easy to do, but kind of wasn't the priority. Now, Enceladus and life. First of all, we are not sure how soon after formation of Earth and habitability life occurred. Probably pretty soon. So 100 million years might or might not be long enough. And the other point is that in this view, the ocean of Enceladus is in steady state. You do get liquid water all the time. If the tides were 10 times too short of heating Enceladus to the present state, then yes, Enceladus could be billions of years old, but only about 1/10 of a time in some kind of cycle could it have liquid water. You have to build up somehow tides and to melt it and then goes back to the frozen state and so on. So the overall amount of energy you put in Enceladus since the formation is not that different. It's just how you distribute it. Is it a chunk of 100 million years or episodes over billions of years.
Thank you. That was very interesting. So one question that I have is the Saturn system is very interesting overall, and one of the things that makes it also interesting is the fact that two of the moons that you mentioned, Dione and Tethys, have Trojan moons, companions. So does your model have anything to say about that fact?
Yes. So the Trojans seem to know what the orbital inclination of the major moons is. So the Trojans of Tethys are inclined by over a degree, and the Trojans of Dione have lower inclinations. And interestingly, this is not nurture. This has to be nature, because the actual orbital, the plane they want to be in, if you break them up and want to put them together, is the plane of Saturn's equator, because not the plane of the orbit of the bigger moon. So the best explanation is that they're younger than the big moons, and they're made of stuff coming off big moons, and in which way they would inherit their inclination, which means that some of the smaller moons are even younger than the major moons, which is not so surprising, but would involve Trojans too. Yeah.
I just wanted to thank you for the various musical references. I'm a physicist and a musician both, and years ago when I read Kepler, I was fascinated to read all the material on the harmonic of the spheres put in there with the elliptical orbits.
Thanks. I'm tone deaf, but this was a good analogy, so it worked.
Could you show us the equations you used to get these results?
Okay. Actually, it's not that complicated, because most of it is.
Well, I don't know. Are they differential equations or?
Yeah, they are.
Or algebraic ones?
Well, first, this is numerical.
Or
this is
what?
all numerical. So you put it in a computer, right? So basic motion is Keplerian, right? So
how many states or whatever are you integrating?
States?
Yeah.
Well, so what the integrator does is, so it advances Keplerian orbits and gives them kicks now and then. And these kicks can be perturbations from other bodies, or tidal forces, or perturbations from Saturn's shape. Those are basic types of kicks. And those are calculated in Cartesian coordinates over a small chunk of the orbit. And it's interesting that they the errors cancel each other out after long periods of time. So we can do this efficiently. And so it's a pretty simple physics. Like when it comes to damping of eccentricities, for example, we put a radial force that goes against the radial motion of the moon. As it's on an eccentric orbit, it goes in and out a bit. So we have a force that fights it, and that simulates kind of the inelasticity of the moon fighting the tides. And for the Saturn tides, we just have a force pushing the moon forward in its orbit, depending on what the tides should be. So the equations are not scary. It's just the time scales and the numbers of bodies.
I have a related question, I think, that maybe you partially answered about the numerics. You mentioned chaotic dynamics. Do you have to do anything special to make sure you're accurately capturing the nonlinear dynamics of these systems?
But the only thing we do is run it many times and then see what the trends are. When some things are chaotic, like when the resonances start overlapping, every time you do it, you get something different. But in the end, you get certain distribution, and you want to make sure that you capture that distribution of outcomes properly.
Well, do you do a check? I mean, you mentioned you don't do the future, but an obvious check on the numerics is if you do a run and then reverse time, do you recover the initial state?
That is impossible, because I think in one slide I had, when you go through resonance one way, it's anisotropic. You cannot, if you go backwards, you get something else. Because if you go into resonance if the inner moon is catching up with the outer moon and they hit a resonance, you can have capture. If it's the other way around, they'll jump through, and that's just the nature of the dynamics. So we cannot, for some problems we can go backwards. For resonances we cannot. The one thing that I did some other resonances which have been studied analytically, and which are simpler because they don't have chaos. And I get the same results that people got pen and paper. What makes me most relaxed about that there is no error in the code is that actually none of the things in here are very complex. It's just that the way they're put together and everything interacting with each other. So you would have really bad things happening if you run this code for a long time, even without resonances, if something was wrong. So,
okay.
Yeah.
And one last thing about the numerics. Do you have to take into account the general relativity, the precession effects, like in the orbit of Mercury, or is that totally negligible?
No, in this case, it's all Newtonian. Orbit of Mercury is the only place in the solar system where we have to do that.
I'm going to show my ignorance here, but one of the key parameters in your simulation is the coefficient of dissipation of Saturn, right?
Uh-huh.
How well this is constrained, and what kind of assumption do you take? You assume is stable and constant all during these 100 million years? So that means you're not assuming any evolution of the interior of Saturn?
That's right. Well, over 100 million years, there might not be much. But apart from us assuming it's constant, it's also the bigger assumption is that we assume that the lag angle is the same for every moon, as opposed to lag time. And that was, I started out that way and was hardwired into the integrator. So I have to, that's something that could be different. That it's not a big deal for Tethys, Dione and Rhea. Once you get closer to the rings and the moons start being, or moon's orbital periods start being comparable to spin of Saturn, that does matter.
Thanks, Matija. It's a very interesting talk. A question about the extent to which you can extrapolate these findings into other systems that have rings. So Uranus has rings. Is there any reason to believe that ring systems are indicative of some kind of cyclic pattern of moon creation and destruction?
Well, Uranus has much fainter rings than Saturn. And it's possible that moons of Uranus are also not primordial. I haven't done that, and that's since we're always looking for things to propose to do, that's an excellent thing to propose, but doesn't look particularly young. And how old it is would be an interesting thing to check. But the big picture would be, and that's pretty naive because I haven't actually looked at Uranus, is that the rings like those of Saturn get darker and thinner over time. And after maybe a billion years, you end up with something that's still there, but has much less mass, and it's much darker. And maybe that's what happened to Uranus.
Do you know of any geological follow-ups, any studies happening right now to constrain the ages of the moons? And if so, do you know exactly how they're planning on doing that? Yeah.
So the geology of these moons, the most important thing about the geology is craters. They're all over them. And even these moons that I say they're young, they're covered with craters. And why that is okay is that craters can form in very short time as long as you have enough impactors making those craters. And if you break up the system and put it back together, there'll be lots of junk flying around, enough to make craters, especially if you have some later events like the one in which Trojan moons were formed. They would form more craters on the big moons. Now, it's hard to distinguish craters made by comets and those made by debris around the planet, because cometary craters can give you age. You count them and you know how many comets there are, and you can figure out the age. If it's all local stuff that gets made and disappears quickly, then it doesn't give you anything about the age. We are now fortunate to have the observations from New Horizons from Pluto and Charon, which can give us pretty much the distribution of comets, because there it's pretty much Kuiper belt objects, that is comets, that are cratering those two bodies. And then we can look at the craters on Saturn's moons and say, oh, does it match in terms of distribution of sizes, comets or not? And so far, from what I've talked to people, the answer is not. You need something else to explain the craters on Saturn's moon. So that's one way, one thing you can do is just see how many different sources of impactors you need. And in this view, the outer moons, like Iapetus, that's very far from the inner system, would mostly have craters from comets. So people are working on that, but I'm not one of them. I'm sticking with orbits.
Okay. Saturn has a spin axis, which is precessing, I think, with a fairly long period.
Yes.
How does that period of precession compare with other periods here?
That's an excellent question. I ignored it. I have Saturn's spin axis be constant, and it actually precesses around the 2 million year timescales. It's way longer than all the other periods, so it's probably justified. For Earth, I also do Earth-Moon system, and you can't do that because precession is much faster. The precession of Saturn carries the moons with it. So the only case in which it has physical meaning is if something outside is affecting the moons and cares about which way the orbital plane is. And the orbit of Saturn around the Sun shifts around at 50,000 years, much faster. So since the timescales are so different, I think it's justified to ignore the spin pole precession of Saturn.
Oh, okay. And the other thing is, I think Rhea is more massive than all the other inner moons put together, and then Titan's an order of magnitude more massive yet.
Yes, that's right.
So so they would somehow dominate effects.
Dynamically, the orbits of the inner moons, all of them, out to Iapetus, are dominated by Saturn's bulge. The fact that Saturn is out of round. And then, so is Titan, because Titan cannot perturb itself. Then Iapetus and Hyperion already feel Titan as a major perturber, and the Sun. But for these guys, Rhea in interior, it's really Saturn's shape that is most influential.
At one point you said that the estimate for the tidal force from Saturn is off by a factor of 10.
Yeah, the old estimate.
How do you get that wrong?
Well, that estimate came from the assumption that the moons, the inner moons, including Mimas, are as old as the solar system. So that was an assumption that was made in the absence of anything else, but turns out to be wrong after the fact.
Yeah, so the tidal force from Saturn is not computed from some model of the internals of Saturn.
It's an excellent question, and after they decided what it was, there were models produced. And there was some actually disagreement back in the circa 1980. I was surprised, it was before my time, that people actually disagreed what it is, and but then it settled kind of that it's probably the tides are relatively slow, and now it's back to it. It looks like Saturn has stronger tides than Jupiter, which is interesting. So people are trying to tie that to the size of the core, that maybe the core is where much of the tides come from, because Saturn has a bigger core than Jupiter.
Well, so the people in this field, and you run an Inbody simulation, basically. Yes. That's what's going on. So everything's got an inverse square force field, and you're integrating the velocity and position out, right? So a couple of questions. So is there kind of a standard tool in this field that everybody uses, or does everyone homebrew their own? Or
depending on what you do. If you do asteroids and comets, there are standard tools that are very good. And they've resolved the issue of what happens when two things come close together, which can be a problem. Like when orbits are well separated, it's easy, but when they have close approach, you have to take it with care, treat it with care, and the standard tools do that. However, I couldn't do that for the Saturnian moons because we have a system within a system. Saturn orbits the Sun, and then we have moons orbiting Saturn. So that's two levels of system. And then we have these tidal forces, which I needed to put in, which are non-standard. So for this problem, I wrote my own integrator. But when I do asteroids, I often use off-the-shelf integrators.
Oh, okay, so the physics is the inverse square force field, but then are there some other physical parameters that are kind of not quite known that well about elasticity of the moons or viscosity?
Yes.
Is that going to change your results a whole lot? Like if you said, if I doubled the viscosity in Rhea or something like that, would that make a huge change to these results?
Yes, I guess I had time to put more stuff, but it seemed to me like a bit too detailed, but we have that in the paper that we try different parameters of the moons. And not just that they are known, but they are expected to change, because if a moon is a solid ice that has one amount of elasticity and so on, but then if you melt a layer within it, then it's going to behave completely differently. So we tried all these things, and you would assume that anything that gets very eccentric would melt like Enceladus inside. It might have a liquid layer, which makes tides much stronger, because that, well, at least the moon responds to tidal forces exactly, because if the shell is not supported but floats on top of the ocean, it would deform much more than it would otherwise. Yeah, we took that into account, and it has an interesting side consequence, which is not so important in the context of this talk. But if you try doing slow tides, you might not be able to cross many of these resonances, because you make moons eccentric, and then the tides within satellites, if they melt, become so strong that they fight the moons, and then they diverge, go away out of the resonance in the wrong direction. So it does matter, but for tides I used here, which are relatively strong, they always manage to push the moons through the resonances with more or less eccentricity and inclination. But yeah, the big part of the project was trying different things and seeing what the consequences were.
Does this process homogenize the material among all these moons, or does the material fractionate before reassembling? And is there any way of verifying all these results from information on the composition and how homogeneous these moons are with each other?
Yeah, that's an excellent question, and I cannot answer that theoretically, but I know what the right answer is, and that is doesn't homogenize, because they are actually all different. Mimas is block of ice more or less, and then Enceladus has much more rock, and then Tethys is more icy, and Dione has more rock, and so on. So it doesn't, and probably there might have been fewer moons beforehand, and their cores might have stayed somewhat intact, and then as the moons are mixed and matched, they end up with different amounts of rock and ice.
Okay, any others?
Let me go back to Dave Morrison's question.
Mm-hmm.
So I appreciate it's not easy to work backwards through all this event, but what kind of, you said the primordial moons would have been stable. I mean, if they were bigger, and if Saturn's Q is so low, right? I mean, say a little bit more about how stable they could have been and what configuration they could have been in to really allow them to last this long with a Q of 1700.
Well, depending where you start. If you start with a compact system, they would reassemble every couple 100 million years or so. But then, if the previous system was very similar to the present system, then they can live for billions of years, because Rhea would move very slowly, and if it has it ran into a Vection resonance, that is the resonance with the sun, at some point. That's we think was the source of the instability in the system. But apart from that, it orbits shifts very slowly at the present distance. So,
because they're so small, but you have this problem of the divide to 3 and all this kind of stuff, right? So the current system. So I guess what you're envisioning is systems that are not too different from this.
Yes,
particular
at least
system.
the previous one, yeah.
Previous one could have been stable for a longer time if it wasn't too different from this one.
Exactly. So, depending on how it started out, it could have had many shorter cycles before it's spread out and settled into the present state. Yeah?
Earlier you mentioned that in general, moons face the planet.
Yes.
Is that irrespective of the distance from the sun?
From the sun, yes. From the planet, no, because it's tidal forces that spin them down. So on one of the slides I had Phoebe, which is the outermost major moon, so to say, and it doesn't face Saturn. It spins every 9 hours and goes around every 2 years. And it's just that the tides are trying to slow down their rotation, and tides fall off faster than other forces. And if you're too far from a planet, that won't work anymore. So the really distant moons do not face the planet.
The irreversibility is a simple consequence of the second law of thermodynamics, isn't it? As soon as you introduce dissipative forces like tides.
Yes, I think that's a part of it. We don't think of it that way usually because just we think resonance works one way, and the other. But yes, since to have the capture process at all, you need dissipation. So yes, it is reversible.
What is the temperature out at these distances from Saturn?
Oh.
10 Kelvin?
No, way more. What's the temperature? Anybody knows?
85 Kelvin. So you mentioned ice. The vapor pressure of water is low at 85 Kelvin, but it's certainly not zero. And the rate of loss of water from solid water into water vapor could very well play a role in lifetimes and in some of these dynamics.
Yeah, once there are moons, I mean, they would apply more to rings than moons because they have so much more surface area versus mass. For moons, well, depends how hot they are, right? Also, like because there could be internal heat, and then Jeff is okay. Yeah. It's too low. Yes?
I might have missed the answer to this question, so sorry if I'm making you repeat, but is there nothing in the cratering of these inner moons that indicates an age higher than 100 million years?
Well, they're covered back to back with craters, and all of the moons of Saturn, both inner and outer. But the size distributions of craters, that is this characteristic distribution of how many big ones versus how many small ones, vary from moon to moon. So it doesn't look like they've been cratered by the same population, so that you cannot use the rate of impact by comets to date them.
All right. Did you have something programmatic, Bill? All right, well, that may be our liveliest question session on record. Let's thank Matija again, and Bill has an announcement.
Thanks, Matija. That was wonderful. And as you may or may not be aware, that was based on published work that Matija has done. We've also just released, and you'll see it up on our website in the next couple of days, the February proceedings of the SETI Institute. So this is a place where we collect and cite all of the articles and publications from our scientists and kind of summarize the work we did in the month of March. The February report is already there. So if you're interested in kind of the breadth of research and the papers and publications of the Institute scientists, you can check on our website and find those February report and the March report again in the next couple of days. I just thought I'd take advantage of the opportunity, since we ended more or less on time, in spite of a wonderful Q&A session, to just highlight some upcoming talks that are coming our way. So the next talk, I had it and lost it. We will have a talk next week on cosmology, and let me just pull that up again. Okay, so next week's talk is The Twisted Universe, the cosmic quest to reveal which end is up. So that should be interesting. That's with Brian Keating from UC San Diego. So if you've got some friends who are interested in the bigger picture and cosmology, please be sure to let them know of that talk. On April 26th, the talk will be from one of our own friends here at NASA Ames, Pamela Markham, who will speak about the Sophia Observatory, revealing the hidden universe with airborne science. So this is the Stratospheric Observatory for Infrared Astronomy, or SOFIA aircraft, that flies out of Palmdale, and on which we have a program for educators that is run on behalf of NASA by the SETI Institute. And then, as a reminder, we have the special event coming up on Tuesday, May 3rd, which is a panel session featuring several scientists from the SETI Institute, including Natalie Cabral, who heads our Carl Sagan Center for Research, and Seth Shostak, who's our senior astronomer. And that will be a panel session where we'll be addressing the question, when will we find life beyond Earth? So lots of interesting discussion and debate, hopefully, and some lively Q&A in that session as well. And on that particular day, lunch will be served thanks to our friends at Microsoft. So it'll probably be full. If you're interested in coming, be sure to get here early. And it'll be also associated with this event coming up that same day, which is Silicon Valley Gives. This is a day in which the nonprofit community in and around San Francisco, Bay Area, and Silicon Valley reaches out to the Silicon Valley community and say, if you like what we do, please support us. Thank you once again for your attendance. Appreciate it.